acid strength and molecular structure. Why are some hydrogen-containing molecules acids and others are not? Why are some acids strong and others are weak? You may have had these questions. We're going to answer them now. So H2S versus CH4. In the way this is written tells us it's not an acid, but it's a nonmetal with hydrogens. Why is H2S an acid and CH4 not an acid? HCl versus HF. Why is HCl strong and HF is weak? What's going on here? First, we'll look at the binary acids. That's a hydrogen and one nonmetal. So we're going to look at the bond between the hydrogen and the generic element, the other thing, like the F or the Cl. So H-Y. In order for this to act as an acid, this hydrogen must be donated, the proton. And so the strength of the acid is going to be affected by this bond, by how strong the bond is and by the polarity of that bond. So in order to be acidic, that bond has to be polarized, with the hydrogen as the positive end and the other element as the negative end. So we need some difference in electronegativity, right? The hydrogen has to be lost as a positive ion, and so if this is already partially positively charged, it's much easier for that to happen. So if we look at the bond between hydrogen and lithium, there is, this is a dipole, there's a polar bond here, but lithium is the positive end. So this is not going to be acidic. In a hydrogen-carbon bond, this is a nonpolar bond. If you didn't have Chem 1A with me, the way I explained polarity was if you have two identical elements, that's going to be a nonpolar bond, kind of like, well, duh, because they're the same, right? If you have two nonmetals that are different, this is not always true, but it's good enough. Assume that it is polar. And the one exception that I asked you to remember was hydrogen and carbon, because this comes up so much, it's so present in organic chemistry. The hydrogen-carbon bond is nonpolar because the difference in electronegativity is only 0.4. So because this is a nonpolar bond, a carbon-hydrogen bond is not acidic. Here, HF, the fluorine is more electronegative. And, we don't need to know their numbers. All we need to know is that fluorine is the most electronegative. And as you get closer to fluorine, things get more electronegative, right? So here's fluorine, very electronegative, pulls electron density away, leaving this as partially positive. So that can fall off. It's acidic. Any questions yet? So the stronger that bond, the weaker the acid. Because if that hydrogen is held onto very tightly, it's less likely to come off. For an acid to be strong, it has to lose its proton. All the time, always. And so this is where strong, weak can get a little bit confusing. It's like, okay, well, if the bond is strong, then the acid is weak. Backwards. So you could think of it this way. So these are strong acids. Oh, that, in my head, this is going a different direction than I anticipated. I don't know if I want to go there. My analogy maker is making noises in my head. So if this bond is weak, then this will lose the hydrogen easily. But that makes it a strong acid. So think of it this way. We talked about the hydrogen as being a baby, and this the original acid is the parent, right? And when it acts as an acid, it hands off the baby to someone else. Chlorine is a very strong parent. It's totally cool, totally confident with letting someone else babysit the child. Because chlorine has a life, right? And sometimes needs to do things without the little bundle of joy. Fluorine is a weak acid. Fluorine's like, nah, I don't want to let go, right? Because it's insecure, it's weak, right? So it holds on tightly to its hydrogen. Does that help? I don't know, maybe not. That's all I got. So here is a little section of the periodic table. So when we go across, we get increasing electronegativity. So fluorine is more electronegative than oxygen. And so this is more acidic because the bond is more polar. When we go down, we get weaker bonds and stronger acidity. Why are these bonds getting weaker? Because the elements are getting bigger, right? So you've got this big old iodine molecule, and it's like it can barely get its arms around to hold on to the baby, right? It's just really big. In terms of bonds, we're looking at the distance between the nuclei is longer, and so the bond is weaker. Hydrogen cannot get as close to iodine because it's got all these electrons in the way. So as we go down, the elements, oxygen, sulfur, selenium, tellurium, get larger, the bonds get weaker. That means that the acids are stronger. This is not a huge deal, but it will come up on an exam, and this will come up again in OCHEM. What about the oxyacids? Well, in the oxyacids, we've got that hydrogen is actually bonded to one of those oxygens. So here's our generic example, HOI. So this is our like chlorine or iodine or whatever, could be carbon. This is bonded to oxygen, which is bonded to hydrogen, and then it can be bonded to other things as well, maybe other oxygens. So what we're looking at here is the strength of this bond is affected by this bond, which is affected by the electronegativity of Y. If Y is very electronegative, it's going to pull electron density away from the oxygen. It pulls electron density away, and that makes the hydrogen-oxygen bond weaker than it was before. It's easier for that hydrogen to come off. So it's going to be stronger. So here we're looking at HOI, HOBr, HOCl, and electronegativity. So chlorine is more electronegative than bromine or iodine. So chlorine is going to pull more electron density away, making it easier for that hydrogen to be given away. So it has a larger Ka. It's still small though. This is a weak acid. It's still small. Then the number of oxygens bonded to that central atom also have an impact. So here, looking at all the relatives of chloric acid, right? Perchloric, chloric acid, chlorous acid, and hypochlorous acid. Right? They differ in how many oxygens are bonded to the chlorine. Each of these oxygens is going to pull electron density away. So the chlorine is pulling electron density away from the oxygen, and these guys are helping out by also pulling on electron density. Okay? So as a result of all this pulling and tugging, this bond is really weak when there's lots of oxygens. And so that's a strong acid. Chloric acid, we've got two oxygens along with the chlorine, pulling electron density away. So this is pretty weak. This equilibrium constant is 1. So that one like balances in the middle. You got half ionized and half not ionized. As we decrease the number of oxygens, this bond gets stronger and the acid gets weaker. So from that information, we should be able to answer questions like this. Which of the protons shown in red is more acidic? Which one is easier to come off? So easier to come off, are we looking for the stronger bond or the weaker bond? We're looking for the weaker bond. We're looking for which of these bonds is the weakest. That one will be the most acidic. Well, what do we have going on here? This is oxygen bonded to carbon. Oxygen bonded to carbon. So that's the same, right? What's different is that this carbon has an oxygen on it. This carbon just has 2 hydrogens. So this oxygen is going to be pulling electron density away from this oxygen, which is going to weaken this bond compared to that bond. That's something you're going to have to wrestle with. It's not something that's obvious. Any questions? So let me just kind of go rogue here. So here we have HF, HCl, it's Br, right? And HI. And this is H2O. So I told you to memorize the strong acids, right? These guys are strong acids, right? So as we're going up, the atom is getting smaller and more electronegative. It's going to hold on tight to that. So this is the weak acid of that group because it holds on more tightly to the hydrogen. With the oxyacids, I think I got paused a long time ago. So this is the strong acid because I told you to memorize it. Well, let's look at the pattern here. Is it the one with the most oxygens or the least oxygens that's strong? The strong acid has the most oxygens. Okay, so by memorizing those strong acids and by looking at a pattern, you can reason out this whole business, even if you can't really explain where the electrons are going or anything like that.